Assalamu alaikum, salam sujatra, and welcome to this Masterclass Explainer. I am your SM015 professor, and I hope you've got your pens, notebooks, and calculators ready. Today, we are conquering Chapter 3, Sequences and Series. This is a massive core pillar of your matriculation math, and we are going to absolutely master it together.
But hey, before we jump straight into the pure math on the whiteboard, let's think about biology for a second. Think about how a zygote develops in the womb through cell division. You start with a single cell, which divides into 2, then 4, then 8, and so on. It perfectly illustrates a sequential pattern happening right in real life. Math isn't just random numbers on a page. It is literally the language of the universe unfolding around us.
Here's our agenda for today's session. We'll cover 5 key learning outcomes: sequences versus series, mastering arithmetic progressions, mastering geometric progressions, linking terms and sums, and finally the big one, the sum to infinity.
Let's start with Section 1, Sequences versus Series.
We're going to clear up the most common, easily avoidable mistakes students make every semester, confusing a sequence with a series. Mixing these up in the exam hall will definitely cost you precious marks. Now, a sequence is just an ordered list of numbers separated by commas. Think 2, 4, 6, 8. But a series, that means we are actually adding those numbers together. You'll use plus signs, 2 plus 4 plus 6 plus 8. So remember this rule. Sequence means commas, series means addition. Simple, right?
Now, whether you're dealing with a sequence or a series, it can either be finite or infinite. Finite just means it ends. You have a very specific set number of terms. But if you see those 3 little dots at the very end, the ellipsis, that tells you the pattern goes on forever. It's infinite. Always watch out for those 3 dots in your exam questions.
Moving right along to Section 2, Mastering Arithmetic Progressions.
In an arithmetic progression, we move from term to term by simply adding or subtracting a constant value. But before we even think about memorizing formulas, you absolutely must know your key variables. A is always your starting point, your very first term. Then we have D, the common difference. This is the constant value you add to get the next term, and you find it simply by taking the second term and subtracting the first. We also have N for the number of terms, and sometimes L for the last term. Nail these down and the math basically does itself.
You're going to want to memorize these formulas. They are your ultimate toolkit for arithmetic sequences. If you need to find a specific single term, let's say the 10th term, you use the TN formula. But if you want to find the total sum of all those terms added together, you switch to the SN formula. And there's also an alternative SN formula you should know. If a question gives you both the first term and the last term, use that alternative one. It saves so much calculation time, and exam time management is everything.
Let's see how this actually builds up in a real-world scenario. Imagine a massive amphitheater with 50 rows of seats. The first row has 30 seats, and every single row after that adds exactly 2 more seats. That right there is an arithmetic progression. Our A is 30, our D is 2, and our N is 50. By applying our SN formula to this problem, we find there are exactly 3,950 total seats. See how quickly we solved that without having to count every single row one by one?
All right, Section 3, Mastering Geometric Progressions.
Now, instead of building patterns with addition, geometric progressions are built purely on multiplication. We're swapping out our common difference for a common ratio, so instead of D, we now have R. And we find R not by subtracting, but by dividing a term by its previous term, like T2 divided by T1. Here is a crucial exam tip. R can never be exactly 1. Why? Because if you look ahead at the sum formulas, plugging in a 1 would mean dividing by 0, which completely breaks the formula and makes it undefined. Keep that tucked away in your mind.
We actually have 2 different formulas for the sum of n terms, Sn. How on earth do you choose which one to use? Well, always check the value of your ratio R first. If R is less than 1, use the formula starting with 1 minus R. If R is greater than 1, use the formula starting with R minus 1. The golden rule here is to always put the bigger number first in the denominator. This ensures your sum calculation stays positive and saves you from those silly, totally avoidable calculator errors.
Let's put this into action with a situation you might face one day, buying a car. Let's say you buy a 60,000 ringgit car and it depreciates, meaning it loses value, by 10% every single year. That means every year it only retains 90% of its previous value, making our R exactly 0.9. If we want to find out the car's price after 12 full years, we actually need to calculate the 13th term. Crunching those numbers, our T13 formula reveals a value of just 16,945 ringgit and 78 cents. Ouch. That is the brutal power of geometric depreciation.
Moving on to Section 4, linking terms and sums.
Okay, students, listen up, because this right here is a secret weapon. So many students forget this during their SM015 finals, but it links everything together so beautifully. Write this golden rule down right now. Tn equals Sn minus Sn minus 1. What does that actually mean? It means you can always find a specific, individual term just by taking the total sum up to that term and subtracting the total sum up to the previous term.
It's incredibly logical once you think about it. If you have the total sum of all terms up to n, and then you literally just chop off the sum of the first n minus 1 elements, what's left? The only piece left standing is the exact nth term you were looking for. It's pure logic, neatly packaged into one super powerful equation.
And finally, Section 5, the sum to infinity, the final boss of this chapter.
This is where mathematics starts to feel a little bit like magic. Think about this for a second. How can a sequence that goes on forever, literally stretching into infinity, possibly have a finite measurable sum? It sounds completely impossible, right? If you keep adding numbers forever, shouldn't the answer always just be infinity? Well, not quite. If the numbers you are adding get smaller and smaller rapidly enough, they actually eventually converge, settling into a single, solid number. Let me explain how.
The formula for the sum to infinity, S infinity, is elegantly simple. A divided by 1 minus r. But wait, there's a massive condition here. This formula is strictly valid only when the absolute value of your ratio r is less than 1, meaning r must be a fraction somewhere between -1 and 1. If it is, the series converges, and you can simply divide your first term a by 1 minus r to find that exact limit.
And this isn't just some abstract theory. It's an incredibly useful tool. For example, we can easily convert annoying repeating decimals into neat, clean fractions for exam questions by treating them as an infinite geometric series. Let's walk through 3 simple steps using 0.03 repeating. First, we break it down into an infinite sum. Second, we identify our a as 0.03 and our ratio r as 0.01. And third, we just apply our sum to infinity formula.
When we plug those numbers in, we're basically calculating 0.03 over 1 minus 0.01. That gives us the fraction 0.03 over 0.99. By simplifying that down, we get the final, elegant answer of 1 over 33. Just like that, a beautiful, clean fraction born out of an infinitely repeating decimal.
So, as we wrap up today's Masterclass Explainer, I want to leave you with this thought. If repeating decimals are really just infinite series hiding in plain sight, what other everyday patterns around you are secretly just math waiting to be solved? Master these formulas, understand the deep patterns behind the progressions, and ask yourself, what other endless cycles in your daily life can be conquered with a simple equation? Keep practicing, keep questioning everything, and I will see you in our next explainer.